And although I've been teaching on Zoom, I'm not really an expert at it. So if there's any problem, if you can't hear me, if you can't see my slides, just let me know. I guess with that, so let me just tell you quickly what my plan is to do today. So I want to start off just introducing some background. I'll tell you what numerical dimension is, do a couple examples, give you some history of this problem. And then the rest of the talk is really just going to be working through two examples to see some kind of crazy things that can happen related to numerical dimension. Let me also say before I go on, so part of this is joint with Yuanfu, Heming Liu, and Junsheng Shi. I think probably none of you know them, except I see Yuri's here, maybe he does. So these are three undergraduates at Penn State who took my introductory linear algebra class, and they wanted to do some kind of math project. So I had them do some numerical work about this problem, and I think they've given some figures that really make it a little more transparent what's going on, at least to me. So if you get bored of my talk partway through, I have on the title slide here one of these pictures. There'll be other kind of more fractal looking pictures later on. All right, so let me get started. Everybody can hear me and read the slides. Nothing too wrong yet.
Yeah,
it's good. And sorry, one more technical thing. So I also have set up a camera pointed at a sheet of paper. I'm probably not going to use it too much, but if somebody asks a question or I want to draw a quick figure, I might try to call your attention to this other copy. So I'm logged in with two accounts, but if you go into the gallery view and look for one that's just a sheet of paper, that's where that will be. I'll let you know if I do that before then. Hopefully we will have no technical problem. All right, so let me get started. So numerical dimension is kind of related to the Ataka dimension of a divisor. So let's start with that. So here's our setup. Throughout, X is going to be a smooth projective variety over an algebraically closed field. You know, it doesn't really need to be smooth, but I'm really just working through a couple examples as the main result anyway. So we'll assume it to avoid trouble. All right, so Ataka dimension, as you might know, is related to what happens to the number of sections of these things as you take bigger and bigger multiples of your divisor. If you like line bundles, bigger and bigger tensor powers of a line bundle. So here's what you do. You have this variety X, you have a divisor on X, and you just start looking at MD, where M is an integer, and you take M to be bigger and bigger and bigger. And you ask, well, how does this H0 grow? And the answer, it's a theorem. It's not, it's a bit of work, but you can find it in Lesieutre book. The answer is that H0 of MD as M increases grows more or less polynomially, in the sense that if M is large and divisible, I mean, there exists constants C1 and C2 and then an integer kappa, such that if M is large and divisible, H0 of MD is bounded both below and above by M to the kappa. So it grows roughly polynomially. You know, it's not going to be on the nose a polynomial, but it, you know, up to constants, and as long as M is divisible to avoid issues with torsion and this kind of thing, it grows more or less polynomially. And the degree of that polynomial, the kappa in this thing that I've written here, is called the Ataka dimension of the divisor. So even if you've never heard of Ataka dimension before, you probably know Kodaira dimension. Kodaira dimension is just the Ataka dimension when you use the canonical class as your divisor. So same construction. You look at the rate of growth of sections of tensor powers. All right, now depending on what you're trying to do, this has a sort of annoying property, which is that the Ataka dimension of a divisor is not a numerical invariant. So you can have two different divisors that have the same numerical class, they have the same intersection number with any curve, and yet different Ataka dimensions. So that's sort of low dimensional and maybe not so enlightening example. So that if you're on an elliptic curve and you take a torsion and non-torsion class of degree 0, those count as numerically equivalent. For the torsion class, H0 of MD, as long as M is divisible by the order of the torsion, is going to be 1. It will have a section. So that'll count as Ataka dimension 0. For the non-torsion one, of course, if you take no multiple, by definition, there's no sections of H0 of MD for any M. So that counts as Ataka dimension minus infinity. Maybe a more geometric example to think about for this kind of thing, though, is that you really can write down a concrete example of a divisor on a threefold, where you have two divisors, they're numerically equivalent. One of them is rigid, meaning H0 of MD has no sections other than just the original one with multiplicity M. Whereas the other one moves in a pencil, and so as M gets larger and larger, you get more and more sections. So in that case, this one, the rigid one has Ataka dimension 0, and the one that moves in a pencil has Ataka dimension even though they're numerically equivalent. All right, so often in practice, right, maybe in birational geometry, you're really only given things up to numerical equivalence. You only have a numerical class of a divisor, which makes it a little inconvenient to use Itaka dimension since it's not going to be defined at the numerical level. So numerical dimension, this thing that I mentioned in the title of my talk, is sort of it's supposed to be an invariant that's like the Itaka dimension, but it actually only depends on the numerical class. So in these examples I mentioned here, especially this threefold one, these two things should have the same numerical dimension, even if they don't have the same Itaka dimension. Okay, so what kind of properties should this numerical dimension have? So it's usually denoted by nu. Right, of course, you could just say everything has numerical dimension 0, but that wouldn't be so interesting. So we should make a list of properties that we would want this invariant to have, and then we could try to write down whether or not it actually has those properties. So maybe the most basic thing is that for base point free divisors, it should be the same thing as the Itaka dimension. You could also ask that it doesn't change when you take a pullback. Maybe you want some kind of weak addition. So if you have a fibration, and you have a line bundle on the total space, the numerical dimension of that should be less than or equal to the numerical dimension on a general fiber plus the dimension on the base. So this is something that is satisfied by the Itaka dimension, and you'd want it to carry over to the numerical case. I mean, and it's up to you, of course.
Is it crucial for this property for Itaka that the fiber is very general, not just general?
I think probably you want to do very general, although off the top of my head, I don't have an example for you. It's a good question, but this kind of thing can happen that you have a divisor and there's countably many fibers where it is effective. Even
John, maybe this is the same story as with torsion points on elliptic curve.
Oh, okay, yeah, that's another. Yeah, that's a good point. So just even on a family of elliptic curves, if your divisor is a section, I guess there will be countably many fibers.
On the product. Maybe you just take the diagonal on the product. And
yeah, that sounds good. So I think
countably many times it becomes a torsion, and for a very general, it has one and the same properties.
Yeah, that's a good point. So yeah, I think we probably do want very general. I mean, again, you could. I mean, we're just making a list of properties we'd like it to have. You could ask for general, but I guess it's probably not going to work if that's what you do. Yeah, thanks for that example. I think that's right. Okay, so you might worry. I mean, I guess I didn't list the most desirable property of all is that we want it to be a numerical invariant. So you might worry, okay, we have these properties, maybe just for some reason there is no way to come up with an invariant that has these properties. So it's just not possible to define a numerical dimension. In fact, that's not what happens. In fact, we have the opposite problem. So there's actually, if you go in the literature, I haven't tried to count exactly, but there's 14 or 15 different possible definitions of numerical dimension that have all of these good properties you could want. So it's not, they all look fine. It's not clear which one should be the right definition or even if there should be a right definition. I say 14 or 15, that's maybe making it sound worse than it really is. There's 14 or 15, but most of them are kind of minor variations on each other. There's maybe 3 or 4 basic different approaches you could take to defining numerical dimension. And only a lot with, you count all these variations. All right, so let me give you just a hint of what these different notions of numerical dimension could look like. All right, so the first one and the one that I'm mostly going to be talking about today is by sort of trying to stick as close to Itaka dimension as we can. So here's what we're going to do. We're going to fix a sufficiently ample A. Sufficiently ample is not a technical term like very ample. Basically what I mean is just take some ample divisor A, and then as long as you replace A by a sufficiently large multiple, the answer you get doesn't depend on what multiple you use. So sort of as long as your divisor is sufficiently big in comparison to D, it won't affect your answer. All right, so before what we were doing to define the Itaka dimension was that we look at how many sections does MD have. We looked at H0 of MD. Well, now we're going to change it and we're going to look at H0 of MD plus A instead. So just twist everything by a fixed ample. You're not going to, the M is attached to the D, but not the A. So, even when M is 1,000,000, you're looking at 1,000,000 D plus this, small in comparison ample divisor A that's not getting rescaled. You'll notice I'm also doing a little cheat here, which is, before I just said MD, now I have this floor symbol around it, this round down symbol. So we're also going to, sort of an additional advantage of this definition is that it works well for R divisors. So what this means is, D is an actual R divisor. It's an R linear combination of prime divisors. What this round down of a divisor means is you just round down all the coefficients. So, it's a sum of a number times a divisor plus a number times a divisor. They could all be real numbers. You're going to round them all down to get integers. And of course, once you have integers, it actually makes sense to take H0 of MD plus A. But this wouldn't make sense for an R divisor unless we did the rounding first. All right, anyway, if you don't like R divisors, if that's not familiar, you won't lose too much for now if you just ignore this round down business. Okay, so how did this work with Itaka dimension? The idea was you look at H0 of MD, it grows like a polynomial in M, and the degree of that polynomial we define to be the Itaka dimension. The catch here is that actually we don't really know anything about how H0 of MD plus A grows. So if D is pseudo-effective or something, this is going to be, broadly speaking, an increasing function of M. But if you want to turn it into a number, just given a sequence, how do you extract a single numerical invariant out of it? This is where you start to run into these 14 or 15 different definitions. So here's 3 ways you could get a numerical invariant out of this sequence. So they're called kappa sigma plus, kappa sigma minus. Well, let me give you a minute to read those. Well, okay, before I give you a minute to read those, let me tell you the kind of thing we're worried about. So we don't know that H0 of MD plus A is actually going to grow polynomially at all. So a priori, it's possible maybe it kind of oscillates between M squared and M cubed as M increases. So it follows M squared for a while, shoots up to M cubed, kind of levels off, still increasing until M squared catches up with it. Then it grows like M squared for a while. So it sort of oscillates, it's an increasing function, but kind of oscillating between M squared and M cubed. So there's no obvious reason that this sequence H0 of MD plus A couldn't do that. We don't have a version of that theorem that says it grows polynomially. So, what if it's oscillating between M squared and M cubed, what should our, what should we take as this numerical dimension? What should the degree be? Should it be 2 or should it be 3? So these different definitions here are just picking out your different options for extracting a number from a sequence like that. So kappa sigma plus is kind of the upper bound. So if it's oscillating between M squared and M cubed, then for k equals 3, this lim sup is going to be less than infinity. But for k equals 2, well, sometimes this number on top is about M cubed and you're just dividing by M squared. So the lim sup with k equals 2 would not be less than infinity. So if it's oscillating between M squared and M cubed, this kappa sigma plus is going to be 3. Is this okay? I know it's a scary looking formula, but.
John,
yeah.
This k is always integer, or you allow?
Yes,
real?
great question. I was sort of cheating. So if you look in the literature, these are all defined by Nakayama, I should have said. In Nakayama's book, it has to be an integer. I'm going to tell you an example today, though, where it actually grows like m to the 3/2 power. And so I'd suggest that maybe we should allow some of these to be real numbers instead. Yeah, so the official definition is take an integer k with these properties, but we'll see some non-integral behavior later in the talk. So it's not totally clear what the right thing to do is.
And another question, what does sigma in the notation mean?
Sigma, so this is, I'm not sure why they call it sigma. So this is just Nakayama's notation for this notion of numerical dimension. I think he calls this the sectional numerical dimension or something. So maybe it's related to section.
So it's Greek, right?
Yes, yeah, and that's just a notation. So there's not some variable called sigma that this depends on. Kappa sigma is just a single unit here.
Okay.
Can I ask, is is M again sufficiently divisible, or does it not matter here?
Good point. I think it probably doesn't matter here because of the plus A, but I would have to check Nakayama's book to be sure. I think it doesn't matter in this case.
Okay.
So if the adding this ample mostly eliminates these kind of torsion issues. You know what? You could ask other questions, you know, well, what if, does this depend on the ample? And the answer is not really, as long as, you know, for any ample, as long as you replace it with a sufficiently large multiple to start with, you get the same answer for different amples. So it really
Right,
does
that
just depend
because
on
of
D.
this ample divisor, you already don't have an elliptic curve with torsion and non-torsion divisor D doesn't already provide an example where these numbers are different.
Correct. For an elliptic curve, these things will all be the same. Yeah.
And and is there some easy example which shows that at least some of these guys are different?
No. So that'll actually be one of the main things from my talk, is to show that these things can be different. They were actually believed to be the same for several years.
Can you say once again? They are believed to be the same?
Well, I'll come back to this. There was a mistaken theorem claiming they were the same, but I'll show you an example today where they're not. That's essentially going to be my main result today, is that they're not the same.
And can I ask another question? So these min and max, I mean, if you're letting K be a real number.
Yeah, good point. So it should be infant soup if you're allowing real numbers. Yeah, so officially
not,
this A here is an integer and min and max. Yeah, if you want to allow real numbers, you should take infant soup. It's a good point. Sorry. I mean, but more basically, the question is, how do these things behave? How does H0 of MD plus A behave as M increases? Can we say anything about this sequence? So I'm not even going to, well, I'll probably mention these again, but just sort of the broad question is, H0 of MD grows polynomially. Can we say anything about H0 of MD plus A? Sorry, was there another question here?
I was just wondering, so there was some discussion about allowing real numbers, and you want to allow real numbers for M, or for what?
The question is, could K be allowed to be a real number? So let me give a spoiler for my talk. The main result is I'm going to tell you a D where this H0 of MD plus A grows essentially like M to the 3/2 power. And then the question is, well, what should this kappa sigma invariant be? Should it be 1, should it be 2, or should it be 3/2? So if you use the definitions in the literature, I guess this one is 2, and this one is 1, and this one is also 1. On the other hand, if it's growing like M to the 3/2, maybe it's more natural to just take 3/2 to be the answer. So again, the official definition you'll find in other papers is that K has to be an integer here, but there's some interesting cases where, you know, maybe a real number would make sense. Sorry, I see there was a question from Faye in the comments. It already got answered. Yeah, D, I'm now allowing D to be an R divisor. So with the Itaka dimension, without the round down, it doesn't behave so well for R divisors. Now the ampleness makes it so this round down is less important, and it becomes a good function for R divisors. Sorry, I missed a bullet here, which would have answered your question. I mean, you might worry, I don't know, round down is kind of a strange operation on divisors. It seems like kind of a violent thing to do to a divisor that's near the pseudo-effective boundary, because when you round it, maybe you would leave the pseudo-effective cone. In fact, the ampleness kind of absorbs the small change caused by rounding. In fact, Nakayama checks that if you use a round up instead of a round down, you're going to get the same answer in all cases here. Because it only changes it by a little bit, and ampleness is an open condition, and your ample will just eat that change. So it is now sensible for R divisors. Now, another thing I should say here is that this is a numerical invariant. So for numerically equivalent D and D prime, you'll get the same answer for all of these. So like everything else I'm saying, is done by Nakayama. I mean, essentially the point is that ampleness is a numerical invariant. And so if D and D prime are numerically invariant, you get the same things, but just with a different numerically equivalent ample divisor. but because it's essentially independent of the amplitude. Anyway, there's something to check here, but in fact, this is a numerical invariant of D owing to the presence of this amplitude. Other questions on this one?
Hey, can you say what kind of, what would just, how the kappa sigma plus could be different from the kappa sigma? What does that mean in terms of the growth rate?
So let me draw you a picture. So can you see my paper over here on another?
Mm-hmm.
All right, sorry, I'm logged in twice. So if you can't see this, I have a
No, but
video.
maybe you have to to stop sharing the slides, I guess. No.
Oh, sorry. So it's at least for me, and it's a separate copy of myself in the.
Maybe then we should find you.
Yeah, I don't know if there's a way to make that.
If you go through the top row, then more to the left, there's another John Lesieutre, which is at the moment just a pair of X's.
Uh-oh, did the internet just die?
The problem is that it is very small, so it's.
Okay, yeah, so let me.
You can do this, you can fix this locally on your, I mean, it's not something for John to do, it's something for you to do on your computer.
Yeah, sure. But now at the moment, there are only 2 X's there, right?
Yeah, I have not drawn the plot yet, sorry. So let me just draw a plot of the kind of thing that could happen. So maybe here's a constant times m. Sorry, I'm not going to use this too much. I apologize, it's so small. Here's a constant times m squared. So you can imagine there's an increasing function of m that kind of oscillates between these two. So it goes up quickly, then it goes, sort of back and forth between m and m squared somehow. We don't really know anything about this sequence, so you can't rule this kind of thing out easily. And in that case, kappa sigma plus would be m squared. It's kind of the upper bound. Kappa sigma minus would be the lower bound, which would be 1. So kappa sigma plus would be 2 in this case, and kappa sigma minus would be 1.
And I was speaking about some just a priori possible.
This is just some a priori possible thing about how these could be different.
And as for the
We just don't
spoilers,
know anything about these sequences essentially, so it's a little tricky to convert them into a number.
and do we know, did you finally manage to find an example of something like this?
Where this happens? So I'll mention at the end, I think I have an example. I haven't written all the details down yet, but this kind of thing, in fact, should be possible.
I see.
But first, I'm just going to give you one where at least you get this non-integral behavior. Sorry,
Have you got it?
Oh. All right. Other questions on these definitions? All right, so again, I mean, some of the big questions is just what can you say about these the behavior of these sequences H0 of MD plus A?
Sorry, in this example, the first 2 numbers would both be 2, is that right?
I think probably these 2 are both going to, I don't know, this is all very confusing, right? So in this case, yeah, I guess you're right.
So I was wondering, I mean, it looks like, I'm trying to think, it seems that the first 2 should be the same, but maybe I'm missing, maybe I'm confused. Okay, anyway.
You mean in general, these first 2 should be the same, or just for this specific kind
For
of
the oscillating examples, it seems that the first 2 basically take only the upper curve.
That could be. I don't remember exactly. I think I don't have an example that will separate all 3 possibilities.
Is there any example? I mean,
than this in the original preprint version of Nakayama that a lot of people still use, including me. I think this kappa sigma is defined as the min and the lim inf. So it's really not clear which one you want to use of all these things.
I mean, it seems maybe I'm wrong, but it seems that the first 2 should always be the same, no matter what the growth rate is.
Okay, well maybe. I mean, like if the sequence is m to the 3/2, then I think this is going to be maybe, well, allowing real k or
Yeah, for if you're allowing real k.
Okay, you could be right. So maybe that's a reason. I mean, maybe they are only different if you allow integers. I confess I haven't thought it through too far. All right, let me go on and get to the fun part. But yeah, keep asking me these things if there's more issues here. All right, so let me just, maybe a reminder for many of you, but what's the volume of a divisor? Imagine you have a divisor and you want to, again, kind of quantify how fast does the number of sections of MD grow. Well, it grows at most like m to the power of the dimension. So d here's the dimension of your variety. And the volume is essentially just the leading coefficient on that growth. So if you have a divisor that's big, meaning h0 of md grows as fast as possible, it grows like m to the dimension of x, then the volume is just the coefficient on the m to the d term. And you normalize it by a d factorial just to make O of 1 have volume 1. So if volume is not familiar, you can just imagine this as not that different from h0. Again, like the round down, a good thing about volume is that it also makes sense for R divisors. So this, as I've written it, is only defined for integer divisor classes. For R divisor classes, it turns out that this extends to a continuous function, and so it still works for R divisors also. So you can also imagine trying to define the numerical dimension in terms of the behavior of the volume function. So the one you'll see most commonly is called nu vol of d. That's the maximum k such that the volume is bounded below by t to the n minus k when t is sufficiently small. So again, I gave you 3 definitions in terms of h0 of md plus a. You could make up another 3 definitions of, using volume instead of md plus a. They're all closely related. I don't think anybody has a guess whether those 2 things are different from each other. But you can start to see how you could quickly end up with dozens of conceivable definitions of numerical dimension. All right, so we'll come back to volume again later, but that's the definition. So if it doesn't grow at the maximal rate, the volume is 0. If it does grow like m to the dimension, then the volume is going to be equal to that coefficient. Okay, let me give you an example now showing that these kind of perturbed sections with an ample are a little different than the sections without an ample. I guess some of you already thought through the elliptic curve case. I understand surfaces better. So imagine you took P2 and you blew up 9 very general points. So the anti-canonical class on there, well, what's the anti-canonical class on P2 blown up at 9 general points? It's cubics going through the 9 points. For 9 very general points, there's a unique such cubic. And so h0 of minus kx with m equals 1 is just 1. There's a single cubic in that class. In fact, so if you take the anti-canonical class and you restrict it to that cubic, this cubic has, well, I maybe shouldn't say cubic. The strict transform of the cubic on the blow up has self-intersection 0. So minus kx restricted to that cubic is a degree 0 class on the cubic. And so in fact, minus mkx has no other sections even when m is larger and larger and larger. But any section of minus mkx would have to vanish identically on the curve because of this non-torsion thing. And so the only section of minus mkx is just going to be that cubic with multiplicity m. All right, so the Itaka dimension of the anti-canonical class on this kind of blow up is 0. The number of sections is not growing at all. On the other hand, when you add in this ample, you don't now have this torsion obstruction anymore. h0 of minus mkx plus a, I'll leave it as an exercise, grows linearly in m. And so even though these don't have very many sections, when you twist by an ample, now the number of sections grows linearly. So this has Itaka dimension 0 is what that's telling us. The degree of that polynomial is 0. But numerical dimension, any of those kappa sigma plus, kappa sigma minus, nu vol, all the ones that we've talked about grow about linearly in M. So the Itaka dimension is 0, the numerical dimension is 1. Okay, which is what the next bullet says. So one form of the abundance conjecture is that if you use specifically the canonical class, then these 2 things agree. So the Itaka dimension, the Kodaira dimension, which is the Itaka dimension of the canonical, is equal to the numerical dimension of the canonical. If you know what KLT is, it should be drawing KLT. If you don't, just read it as smooth. Okay, now let me just say one more thing. If you don't believe me that these MD plus A's are ever conceivable to look at, this kind of stuff actually shows up quite a bit in birational geometry. So here's a screenshot out of the BCHM paper on finite generation of the canonical ring. You can see they really do use this kind of linear system in there. These things show up all over the place, and it's maybe a little surprising that we don't understand them so well. So here you can see on this line, there's H0 of the round down of MD plus A. What they needed to know in BCHM is that if you look at that sequence H0 of MD plus A, that if it's not bounded, then there's a linear lower bound. So if it's not bounded, it grows at least linearly. That's actually a theorem proved by Nakayama, and it does show up in here. So, you know, these kind of things show up basically because this extra ample lets you use vanishing theorems from time to time. So here it is in BCHM. You can find it in Kolar-Mori too, although the notation's a little different, so I went with this one. But these twisted sections, these H0 of MD plus A, are a pretty practical thing to use. I mean, I think it's not just a curiosity. Okay, so that's the first sort of strategy to define a numerical dimension, is you should look at sections of MD plus A, or if you'd rather use volume, which is a little easier to handle sometimes, look at the volume of MD plus A, or the same thing, normalize the volume of D plus TA, where T is small. But that's not, in fact, the only approach to defining numerical dimension. So this is maybe not the main theme of my talk. I just want to very briefly give you the idea of how else could you define the numerical dimension. And another approach is using intersection numbers. So this was first done by Kawamata. Kawamata's definition of numerical dimension was that if you have a Neff divisor, the numerical dimension of D should be the biggest K such that D squared is not 0. Sorry, D to the K is not 0. So just as an example, think about if you're on a surface and you have a divisor D that's Neff but not ample. So D squared is going to have to be 0, because if D squared was positive and it's Neff, well, that would at least mean it's big and Neff. I mean, takes a divisor that's Neff but not big, is what I should say. So D squared has to be 0, otherwise it would be big. On the other hand, D to the 1 is not 0, as long as D is not 0. And so if you have a divisor that's Neff but not big on a surface, the numerical dimension is going to be 1. So you're detecting these things in terms of intersection numbers. All right, this doesn't work so well if D is not Neff. You know, if D has a base locus or something, you know, the geometric meaning of self-intersections of D is a little obscure because you get these excess intersection contributions coming from the base locus. There is still a way to define a numerical dimension using intersection numbers. So this is done in the Buxom-Demailly Pound-Peternel paper. And the definition is, it's the same definition. You take the biggest K such that some kind of self-intersection of D is not 0. But you have to use a kind of fancier version of the intersection number. So this is the restricted positive product that's studied by the BDPP paper I mentioned, and also a paper by Buxom, Favre, and Janssen. Roughly speaking, what this does is that if you want to take the moving intersection of some divisors, you just don't count intersections that happen along the base locus. So officially, you have to take some kind of limit over birational models, taking strict transforms. But basically, what you're imagining is you just blow up the base locus until they have no more common base locus, and then you take the intersection number of the strict transform. So as you'd guess, that's no longer a linear form on divisors. This is kind of a messy thing to deal with, but it does have a lot of good properties. It's continuous on the big cone, for example. And in fact, you do get a good notion of numerical dimension out of it by just taking the numerical dimension of D to be the maximum of K such that D to the K is not 0. All right, so that's another way you could try to define numerical dimension in this intersection theoretic way. All right, let me give you one more definition just to give you the flavor. So I'm not even going to give you a correct definition this time because it's kind of technical to do it correctly, and I'm not going to use it again. But the the third notion of numerical dimension, this one's again due to Nakayama, is usually called kappa nu. And the definition is this. So if you have an irreducible subvariety W of X, to say that D numerically dominates it, essentially just means you can move D in its numerical class to make it contain W in its support. Right, this isn't quite right. You know, maybe D is pseudo-effective, but not effective. So, you know, you can't really find an effective representative containing W. So really what you want to do is blow up W and then ask, you know, is MD minus the exceptional divisor pseudo-effective on the blow up? I mean, it's annoying to do it right. And again, I'm not going to use it. So if this sounds intriguing to you, I encourage you to read Nakayama's book where he actually uses this quite a bit. But roughly speaking, so we say it numerically dominates a subvariety if you can move D to contain that subvariety. Then you could define the numerical dimension of D to be the minimum of the dimension of something that D doesn't numerically dominate. So this is a little confusing. I still don't really understand this one. Let me draw you another picture here. Sorry, it looks like my camera has fallen asleep. Hi, everybody. Well, okay, maybe let me not do that. So let me just say in words how this one works. So imagine you take P2 cross P1, and your divisor D is the pullback of O1 from P2. So what is an element of, what do divisors numerically equivalent to D look like? Well, we're going to allow R divisors, but so, you know, you could also be numerically equivalent to D by being 1 over M times something numerically equivalent to MD. So what are things numerically equivalent to MD? They're just, you know, a curve in P2 cross P1. So they're divisors in P2 cross P1 of the form curve in P2 cross P1. So that's what something numerically equivalent to this is going to look like. So what subvarieties are numerically dominated by this D? Well, any curve in P2 cross P1, you can find something numerically equivalent to D that contains that curve, right? Because given a curve, you can project the curve down to P2 and then take that curve cross P1, and that's something numerically equivalent to D and that contains the curve. So any curve is numerically dominated by this thing. On the other hand, you know, not every surface is numerically dominated by it. If you just take some surface, you know, P2 times a point, for example, is not numerically dominated by that class. So this kappa nu is defined to be the minimum dimension of something that's not numerically dominated. Every curve is numerically dominated, but not every surface is numerically dominated. So again, there's some fudging here. You need to add some epsilon times amples and so on. But roughly speaking, that's what this kappa nu is about. Again, I promise not to use this one again. I just wanted to give you the flavor of what it is. Sorry, was there a question? Oh. All right, so let me keep going here. So let me tell you a little more context for this thing. So you might wonder, well, how do these numbers H0 of MD plus A behave? So we were drawing these pictures of this possibly exotic behavior of these things, but it's not actually clear what should happen. So in fact, it was originally, I don't know if Nakayama called it a conjecture, it was a question of Nakayama in his Zariski decomposition and abundance book. But actually H0 of MD plus A is no worse than H0 of MD. These numbers grow more or less polynomially in M. So the question was, do there exist constants C1 and C2 and an integer nu of D such that H0 of MD plus A grows basically like M to the nu? Yeah, so like I said, the story is a bit of a mess. This was proved as a theorem in 2012. In 2016, there was a mistake found in the proof. The same paper gave a new proof that this was right. Unfortunately, it's also wrong. So I'm going to start off today by giving you a counterexample to this statement. So I'll show you a divisor. You know, I'm going to give a completely explicit example of a variety in a divisor where H0 of MD plus A does not grow polynomially in M. I mean, maybe another part of the conjecture was it was conjectured that all these different definitions of numerical dimension, this kappa nu involving numerical domination, this BDPP notion using moving intersection numbers, all these different variations on kappa sigma measuring the growth, it was conjectured that these were all equal to each other, sort of in a related theorem to this one. It was thought for a time that these definitions were all the same, but in fact, they're not all the same, as the example will show. So there's really two main results coming from this example again. So the first is that H0 of MD plus A does not have to grow polynomial in M. Consequence of that is that the different notions of numerical dimension are not equal to each other in general after all.
So your oscillating example is going to come to prove this, right? To disprove this.
Well, just the M to the, as I've stated it here, the exponent was supposed to be a positive integer. And to get, these other definitions of numerical dimension were integers by definition. It's like the maximum K such that the Kth self-intersection is non-zero. So the hope was actually that H0 of MD plus A grows like M to an integer power. So I'll first do an easier example showing that that's false. It can grow like M to a fractional power. Then at the end, and again, I apologize, it's still a little speculative, but I'll show you what should be an example where in fact it oscillates between 3/2 and 2. So this is false even for allowing real numbers as the exponent on the M. But the first part, I'm not claiming this. The first one I'm going to show you, it's bounded above and below by M to the 3/2 power. Other questions? Yeah, let me also note, so the situation was just kind of a mess. In fact, this theorem that this grows polynomially had turned out to be used in an important way because there was actually another wrong result. I mean, there's maybe two versions of abundance. One is that kappa equals kappa sigma for the canonical class, and then the other is that if the canonical class is Neff, then it's semi-ample. These are equivalent to each other, but the proof that they're equivalent actually was relied on something wrong. It was corrected to rely on this. This is also wrong. It looks like Fujino has fixed everything though. So if you're using results related to this stuff, you should tread a little carefully. But as far as I know, the fact that this thing is not true is not going to cause the sky to fall in any serious way. So those two versions of abundance are equivalent again, thanks to this other recent work of Fujino. All right, so let me get started. So a little notation before I get to the example. Soon it's just going to be a fun example talk. So when I write n1 of x, I mean the finite dimensional vector space of divisors on x mod numerical equivalence. The effective cone is just the subcone of n1 of x. It's which classes in that vector space are represented by actual effective divisors. And then the pseudo-effective cone, f with a bar over it, it's just the closure of that cone, so limits of classes of effective divisors. If you haven't seen this before, the example is going to be real easy. I'll draw you a picture soon. All right, a couple other general remarks. So first is that imagine I have a variety and it has a pseudo-automorphism. So what that means is it's a birational map from x to x. It's not an automorphism, it's going to have indeterminacy, but it doesn't contract any divisors in either direction. So neither phi nor phi inverse contracts a divisor. All right, so that's a pseudo-automorphism. It's invertible. Its inverse is also a pseudo-automorphism. And the good thing about pseudo-automorphisms is that they preserve H0. So if I have a line bundle L and I pull back via pseudo-automorphism, the pullback of L also has the same H0 as L did. This is essentially just Hartog's theorem. If you have a section of 1, because this thing is indeterminacy only in codimension 2, if you have the section, you can pull back that section and just extend it across this codimension 2 stuff, and you get a section of the pulled back line bundle. So if you have a pseudo-automorphism, unlike a random birational map for which this is not true, if you have a pseudo-automorphism, when you pull back a line bundle, you don't change the number of sections. You also don't change the volume if you like to think in terms of volume. Maybe I should also say if you take an effective class and you pull back via pseudo-automorphism, it's still an effective class. So that means that pulling back by a pseudo-automorphism preserves the effective cone and the pseudo-effective cone and the movable cone, the Neff cone. Well, not the Neff cone, movable cone. let me stress one other thing. So it doesn't preserve the Neff cone. If you take an ample divisor and pull back by a pseudo-automorphism, it's going to end up with base locus along the indeterminacy of the map. And so the pullback of an ample is no longer ample. It has this base locus. It's probably not even Neff because it'll be negative on curves in the indeterminacy. But the pullback of an effective is still effective, and the pullback of pseudo-effective is still effective. So I just said a lot and slightly garbled questions on these first two bullets at least. All right, so now imagine I have a pseudo-automorphism and it has infinite order. So if I have a pseudo-automorphism, I have a well-defined pullback at the level of numerical classes. And I'm going to assume that that pullback has an eigenvalue that's bigger than 1. So I'm writing that as lambda 1. Some of you will recognize that. That's the notation for the first dynamical degree of phi, which I won't define. So lambda 1 just means what's the spectral radius of this map? What's the largest real eigenvalue of this thing? So if I have a pseudo-automorphism and I have this pullback, and it has an eigenvalue that's bigger than 1, well, think about what happens now if I start with an ample and keep pulling back. So take an ample, pull it back by phi, pull it back by phi again, pull it back by phi again. You've all taken linear algebra. So you know what happens if you start pulling back some random vector under a linear map again and again and again. It's going to converge to the eigenvector associated to the largest eigenvalue, up to rescaling. And so that means that that eigenvector is actually a pseudo-effective class, right? If I take an ample, I pull it back, it's still effective. I pull it back again, it's still effective. I pull it back again, it's still effective. Up to normalization, the limit of those things is this eigenvector class. So that eigenvector class is a limit of effective things. That means it's pseudo-effective. In general, it won't be effective itself, but it is pseudo-effective. All right, so what I just said is essentially some version of the Perron-Frobenius theorem. Still good? All right, so this is, I'll do a specific example of this in a minute if that's confusing to you. So here's what we're going to look at now. So this is an example that I learned from a paper by Oguiso, who did a lot of the calculations, so I didn't have to. So we're going to take a complete intersection of hypersurfaces in P3 cross P3, which are of types 1, 1, 1, 1, and 2, 2. All right, so by adjunction, that's a Calabi-Yau threefold. It's going to be smooth as long as you pick these things generally. The Picard rank will be 2 as long as you pick these things generally. So Oguiso proved that this thing satisfies the Kawamoto-Morrison conjecture, if you know what that is, the cone conjecture. On the way, though, he also did the calculation that I need to. Sorry, let me try again to get my picture up. Because I want to draw you a picture of what does the pseudo-effective cone of this thing look like. Sorry, it just logged me out for waiting too long. I'm almost there, sorry. Any questions while I pull up my camera again?
John, I'm really sorry. Is your camera still logged in?
I think it should be again. Does anybody see it? I had to turn it back on.
Now I see only one.
I think I'm there at the very end of the list. Yeah, sorry, for logging out, I got kicked out.
Oh, yeah, I got it. It just jumped to the place.
Yeah, sorry. So everybody who's still paying attention, I have a tablet just pointed at a sheet of paper. I want to draw you a picture now. You're probably all better at Zoom than I am, but if you're in this gallery view and you just scroll through the arrows all the way to the end of the list, you'll see it. So it's just a sheet of paper with a pen on top of it now.
Yeah, it's to the very right in the gallery, and then you can press the right button and then click to pin this video.
All right, you got it there? It's not really crucial, but I think it's helpful to draw this picture. All right, so here we go. I'm drawing some axes now. Hopefully you can see them. All right, so this Calabi-Yau threefold, I said the Picard rank is 2. So this vector space N1 of X is a 2-dimensional vector space. What are the generators? Well, I could pull back O1 from one of the P3s, or I could pull back O1 from the other P3. And so that's what these two axes here are. So the Neff cone will be spanned by those two things. The Neff cone is just the first quadrant in this picture here. But now here's what you could do. So here's the interesting thing about this variety. That if I take the projection from X down to either one of the factors P3, that's a generically 2-to-1 map. And so there's a covering involution associated to this map. Now there's a catch. This involution is only a birational involution. The problem is that the projection is not actually 2-to-1. There's a few fibers, a finite number of fibers that contain a curve. So the covering involution won't be defined in those fibers, but it is defined everywhere else. So it is a pseudo-automorphism. You know, there's a few curves where it's not defined, but everywhere else it's defined. So I have this 2-to-1 projection down to P3. The covering involution gives me a pseudo-automorphism. I could use the other P3 instead. I would get a different covering involution, a different pseudo-automorphism. You know, each one independently is not so exciting. They're just involutions. But it turns out their composition has infinite order. So this is something that's worked out in this Oguiso paper. So you could, you know, you have these pseudo-automorphisms. They act on N1 of X. They're involutions. And he found that actually the matrices for these things with respect to this basis giving back by pulling back the O1s are these things that I have written on my slides here. Sorry for switching back and forth between the slides. So tau 1, you know, if you just square that, you get the identity. Tau 2, if you square that, you get the identity. But if you multiply them together, you get this new matrix, 35, 6, -6, -1. And that has infinite order. You know, it's easy to see it as infinite order just because it has an eigenvalue that's about 35, 17 plus 12 root 2. All right, so what would happen if I started with an ample divisor and I started pulling it back by this map phi again and again and again? So if, you know, I could take the ample class 1, 1. I could pull it back. So that map here, you can see, does not preserve the first quadrant, right? It's not going to pull back an ample to an ample. It's going to pull back 1, 0 to 35, -6. So I guess down here somewhere. So that's if I pull back by phi. What if I pull back by phi again? Well, it goes even further away from the first quadrant. So I'm, you know, normalizing them to keep them shorter. And if I keep doing that, if I keep pulling back, they're going to get closer and closer and closer to some limit, which is the eigenvector for that pullback. So I'm going to call that vector D1. And you could do the same thing with the inverse map. If you took your ample and you kept pulling it back and back and back again and again and again, it's going to converge to the leading eigenvector of the inverse, which is D2, which is just the same thing flipped around y equals x. Now, because that was effective and that was effective and that was effective and that was effective, all these pullbacks are effective and they're converging to that eigenvector. So that eigenvector is a limit of effectives. It's pseudo-effective. Same thing for the other eigenvector. Is this any objections yet? All right, so here's what I propose.
Maybe the eigenvector, it could be actually effective, not just pseudo-effective, right?
It could be. In this case, it is not. But a priori, I think so, yeah. In fact, this one I should be negative on a set of curves that's risky dense. So there's no for it to be effective.
It is an irrational thing.
Correct, it's irrational, yeah.
It can't be effective because of that, right?
Oh, yeah, okay, that's a good point. That's
Why is it irrational? Ah, we know the eigenvalue, right?
Yeah, we know the
17
eigenvalue
plus
has a
12
2
square roots of 2.
Yeah, I have the eigenvector written down on the slide over here. It's 1 plus root 2 in the x direction and 1 minus root 2 in the y
I
direction.
just missed the slide.
All right, so here's what I propose now. We're going to take this D1, this eigenvector class, and we're going to compute H0 of MD1 plus A as a function of M. All right, now here's the thing, right? Usually if someone just comes up to you with a variety and a line bundle and they ask you what's H0, it's hard to tell, you know, especially if it's not ample. You have almost no hope. There's some complicated base locus. I mean, what are you going to do? How could you possibly compute these numbers H0 of MD plus A that you're supposed to be looking at? But this variety has this extra geometry coming from the birational automorphism group that makes it extremely easy. So let me just point at the picture one more time. So what are these divisors MD plus A? Where are they on the pseudo-effective cone? Well, they're, up to rescaling, it's the same thing as d plus 1 over m times a. So they're very close to d. They're divisors. These md plus a's, as m gets larger and larger and larger, up to normalization, are just sort of clustering around this d1 here. So how are we supposed to compute h0 of md plus a? I mean, right, these are really complicated divisors. Their base locus is really complicated. They're very, very close to the pseudo-effective boundary when m is large. They're really awful divisors. But I claim that, in fact, it's almost trivial to compute h0 of md plus a in terms of m. So let me tell you how to do that. Here's the thing. Any divisor on this variety whatsoever, if you pull it back by the pseudo-automorphism phi, the composition, enough times, you're going to get an ample divisor. Remember, pulling back doesn't change h0. So if you have a divisor and you want to compute h0 of that thing, you pull it back a bunch of times until it's ample. You compute h0 of the ample using Riemann-Roch. I mean, it's even easier because it's a Calabi-Yau, so there is no higher cohomology you have to worry about by Kodaira vanishing. So you just apply the Riemann-Roch formula, for an ample divisor on a Calabi-Yau threefold, h0 is basically just d cubed over 6 plus some lower order term that doesn't matter for us. So let me say that again. Any line bundle, you want to compute h0 of that thing, you pull it back until you get an ample, and then you just take the top self-intersection of that ample and divide by 6. And up to some trivial error, this gives you the correct value of h0. All right, to do that in terms of m, there's still one thing we need to do, which is in terms of m, how many times do you need to pull back md1 plus a to get an ample? But in fact, even that is easy. So
can I ask, when you say any, you said any line bundle, but you mean what? Any effective or what?
Yeah, I guess any big, but it's also easy for the other ones because the answer is 0. So
okay, but in order to get something ample, when you pull it back.
Yeah, that's right. Sorry. So yes, correct. Any big divisor you can pull back via a sequence of automorphisms and get an ample. And then you can compute h0 of the ample. And all these md plus a's that we're looking at are big because md is on the boundary of the pseudo-effective cone, and then that plus a nudges it just a little bit into the interior. All right, so how many times do you need to pull back md plus a to make it ample? Well, this is actually just an easy linear algebra exercise. And the reason is that if you write your divisor in the eigenbasis given by these d1 and d2 on the pseudo-effective boundary, the pullback via phi is just the 2x2 matrix lambda inverse. And in particular, that means that the product of the coefficients is invariant under pullback. So if I have a divisor and I write it, as a combination of d1 and d2, when I pull it back, the product of those coefficients doesn't change. So let's think about this md plus a. How do we write that in terms of the eigenbasis? So I'm going to use d to be d1. I maybe should have clarified on the slide. What is md plus a in the eigenbasis? Well, let's write our ample in the eigenbasis. We'll say it's m1 d1 plus m2 d2. md is just md1. There is no d2. Sorry, d is d1 here. And so, when you write it in coordinates, md1 plus a is little m, that m that we're increasing, plus m1, comma m2, where those are just some constants fixed for all time, depending on what your ample is. So you have this, you're going to pull it back until it's ample. Well, how do you tell when a divisor is ample? Roughly speaking, it's just when the two coefficients are on the same order of magnitude, right? That the ample cone was just spanned by h1 and h2. So to tell if a divisor is ample, it's going to be that it's roughly the same number of d1s as d2s if you normalize them right. So you have this m plus m1 comma m2. You're going to pull it back a bunch of times until these two factors are roughly equal, right? I mean, you're kind of imagining in your head that this little m is very, very, very large. So this first factor is much bigger than the second factor. If you pull back a bunch of times until the two factors are roughly equal, which means you're in the ample cone, more or less what you're going to get is that your divisor in the eigenbasis is the square root of the product, m plus m1 times m2, and then the square root of the same thing again. Right, the ample cone is given by the subcone where the ratio between these two coefficients is in some bounded interval. So, more or less the number of times you need to, after you pull it back enough times to make the two things roughly equal to each other to make it ample, you're going to end up with something like this. Roughly square root of m, square root of m. Is that okay? I'm doing a lot of rounding and cheating here, but it's just the ballpark calculation. I'm also ignoring the round down, which turns out not to matter, although, again, that's something else you have to prove. You know, you might worry that when you round down and then pull back, the error created by rounding down, you know, increases under the pullback. And it does, but not by enough to make a difference. Let me just say this one more time, because this is the fun part here. So m times d1 plus a in the eigenbasis is just little m plus m1 comma m2. You pull it back until it's ample. So you pull back, you preserve the product of these things, but you pull back enough times so they're almost equal. So they're going to end up both being about the square root. And so the ample divisor that's obtained by pulling this md1 plus a back until it's ample is going to be roughly in the eigenbasis square root of m square root of m. Well, h0 of md plus a is h0 of that ample. h0 of an ample, we already said by Riemann-Roch, is just the top self-intersection. So what's the top self-intersection of square root of m square root of m? Well, that's square root of m square root of m. We're on a threefold, so I need to take the third self-intersection. Those mixed intersection numbers are non-zero. You know, d1 squared dot d2 is not zero. So square root of m square root of m, when you take the third self-intersection, is going to end up with a root m times root m times root m. It gets a m to the 3/2 term. So h0 of md1 plus a comes out to be about m to the 3/2, which contradicts this theorem that it was supposed to be m to an integer power. Is that calculation clear? So again, there's a little cheating with the round down, and what does it mean to say roughly equal, but it's not serious. All right, so I want to now keep going. I want to tell you a second example with a similar flavor, and maybe the key observation from this example is this. Sorry, I'm allowed to keep talking, right? I see I'm already past an hour. Sorry, there's a question from Faye, is d1 squared d2 not zero? Yes, d1 squared d2 is not zero. I mean, you know that like d1 plus d2 cubed can't be zero because that sum is ample. So one of those terms has to be non-zero. It turns out, in fact, they're all not zero. But that's how you know that you get this 3/2 coming out. Other questions? Yeah, so it's not in the slides, but this shows that the polynomial growth of h0 of md plus a is too much to hope for. You get this m to the 3/2 business. If you go back and look carefully at those other definitions of numerical dimension, this thing actually has kappa sigma equal to 3/2 if you allow real numbers, or 1 if you don't. Kappa nu, the one defined in terms of intersection numbers, sorry, kappa nu is the one defined in terms of numerical domination, that's equal to 2. And the one defined in terms of intersection numbers is equal to 1. So people had hoped that these 15 different definitions of numerical dimension are all equal to each other. But this calculation with this m to the 3/2 shows that that's not going to happen. In fact, they all have these good properties you'd hope for in a definition of numerical dimension, but they don't coincide in general.
But this is still not oscillator behavior, right?
That's right. No oscillating behavior here. You can write it down. I mean, it sort of oscillates between 20m to the 3/2 and 40m to the 3/2, but it's still an m to the 3/2. Yeah, good point. So I want to now go on and show you something even worse, with the caveat that I haven't had a chance to check all the details yet. So I'll show you some, I'm not going to tell you anything false, but the punchline is not totally checked. But I think these pictures are interesting even if you don't care about the punchline. All right, so let me keep going. So what was it that allowed us to make this computation in that example, essentially? It was that on this variety, you could compute h0 of any line bundle whatsoever just by pulling back until you got an ample and then using the Riemann-Roch theorem. So that was
so question. So what if you don't plus the ample class A?
What if you don't add it there?
Yeah.
I guess no. that one's not effective. So H0 is just going to be constant 0 in that case.
Oh, okay, okay.
Yeah, so this plus A really does change the answer dramatically, even though the MD is much larger in terms of what the coefficients are.
Yes.
All right, so the thing that let us do this was that any divisor whatsoever you could pull back by a pseudo-automorphism, and so you could instantly calculate H0 of any divisor. And that's a nice thing about this example, but in fact, we sort of expect the same thing to work on any Calabi-Yau threefold, I think. If you believe the cone conjecture, there should be some sort of good simple cone, and then the entire pseudo-effective cone is just given by the orbit of that cone under the group of birational automorphisms. So any variety where you know the cone conjecture, I think, again, I'm not claiming a theorem here, I'm claiming a computational fact. If you have a Calabi-Yau threefold where you know the cone conjecture is true, you can essentially hope to compute H0 of any line bundle just by pulling back until you get to some simple cone, maybe a subcone of the ample cone, and then using Riemann-Roch there. So I want to show now what happens if you do that in practice on a more complicated, higher Picard rank Calabi-Yau threefold. All right, so the example I'm going to talk about now are called Euler varieties. Again, most of the hard work has already been done for me by other people, Cantano, Guiso in this case. But I want to show you now what happens to the volume function near the boundary on this other kind of variety. So what is the Euler variety? I'm going to take a hypersurface in P1 to the 4th of type 2222. This is a smooth Calabi-Yau threefold in general, just by adjunction again. This time, though, the Picard rank is 4, not 2, so necessarily all the pictures are going to be a lot more complicated. But in many ways, it's similar. So this thing has 4 different projections down to P1 times P1 times P1. Each of those projections is generically 2 to 1. So again, you get covering involutions. This time you have 4 covering involutions and not just 2. And you can check, well, I mean, it's a little work, but Guiso and Cantà check that the group of birational automorphisms in general is a free product of those 4 Z mod 2s. So it's, I mean, a similar deal. And now the thing is this. So again, any big divisor, you can pull back by some sequence of these pseudo-automorphisms. You can get an ample class, and you can compute H0, or you can compute the volume of any line bundle. So this is what I had these students I mentioned at the beginning, Yuan Junsheng and Heming, work out. I mean, they wrote a computer program where if you put in a specific big class on this Calabi-Yau threefold, it will instantly compute H0 on the nose. And that allowed us to make some fun plots of what the volume looks like. Okay, so let's think about this variety a little bit. So what divisors do we know? What do the positive cones of divisors look like? Well, there's a few obvious good divisor classes on here. So one thing you could do is you could pull back O1 from one of the P1s. Right, it has 4 different projections down to P1. You can pull back O1 from any of them. It's actually going to be, so that's what I've written in this first bullet here. It's actually more interesting if you look at some classes you get by adding 2 of those together. So the pullback of O1 from one of the P1s plus the pullback of O1 from one of the other P1s. So that's a semi-ample. I'll show you a picture in a minute of why it's more interesting to look at these sums than just a single thing. Once you have those, you could also start pulling those back under these involutions. So you have the full orbit of these things under pullback by birational automorphisms. I'm going to call those semi-ample type. I threw the type in there because they're not actually semi-ample at all, right? They have base locus along the indeterminacy that you pulled them back by. On the other hand, they're pretty well behaved. So these are semi-ample. It's easy to figure out how H0 or volume behaves. I guess I'm going to switch over to volume here. But the volume of D plus TA for those divisors, any of them, so it's easy for these, and then it follows for their pullbacks, is that the volume of D plus T times an ample grows linearly in T. All right, now there's some other interesting classes too. We know those semi-ample ones, but you could do the same thing as before, and you could look at eigenvectors. So you could take some fixed word in the generators of the birational automorphism group. Chances are very good that it has an eigenvalue bigger than 1, and you could take the eigenvector associated to that pullback. And just like before, those eigenvectors are going to be pseudo-effective classes. By almost the same argument we did before, any eigenvector class of this type is going to have volume grow about like t to the 3/2 power. So I've switched to volume instead of h0. Sorry, go ahead.
Yeah, sorry. What is BIRX?
That's the group of birational automorphisms. And in this case, it's just generated by those 4 involutions.
Okay, well, and what is D?
So here, I mean, D is anything that's in the orbit of these divisors under birational automorphism X. So if D is semi-ample type, by which I mean, you know,
Oh, I see. It's a form of the semi-ample class above.
Yes, yeah, that's right.
Okay.
So
Yes.
if D is a special divisor on the boundary, which is gotten by taking this and pulling it back under a birational automorphism, that's right. If D is like that, then the volume of D plus TA grows like this. The numerical dimension is 2. If D is an eigenvector, and again, the eigenvectors are also on the pseudo-effective boundary, then the volume grows like t to the 3/2 by almost the same calculation as before. So those are, at least to me, the obvious divisors you can write down on this space. Is this good? Let me show you these pictures. So here's what we're going to do. So the Picard rank of this is 4. It's hard to plot, but I can take a compact slice of the pseudo-effective cone, and that's now going to be some convex 3-dimensional body. So that's what I've drawn here. So what these guys did was they took all words up to length in this picture, I don't know exactly, maybe up to length 8 in the generators of the birational automorphism group. They computed what the eigenvector is, and then we just plotted all of them. So this is all the eigenvector classes. So this is some kind of approximation to the pseudo-effective cone of our variety. And you can see it's a kind of complicated fractal type object now, but it's a...
So
again,
the
this
class is marked here if it is an eigenclass for at least one birational self-mark.
Sorry, what was the question? Was
did I get it right? So what is drawn here is every class which is an eigenvector for at least one birational transformation, right?
correct? Yeah. So we made a list of all 10,000 pullback matrices for short things in the birational automorphism group and plotted the eigenvectors. That's right. It's a list of all the eigenvectors for pullback by a birational automorphism. Because this is a Calabi-Yau, I should say every birational automorphism is a pseudo-automorphism. So that's why I'm switching between pseudo-automorphism and birational automorphism without getting in trouble.
And does the picture has a fractal structure?
Yes, that's right. So you'll get smaller and smaller circles packed in here. All right, so this is the eigenvectors. There's these other classes that I was calling semi-ample type. Let me show you what happens when you add those into the picture. Right, sorry, so looks like I changed my perspective slightly, but they show up anywhere 2 of these circles in our eigenvector picture are tangent. One of those semi-ample classes is living in between them.
Sorry, John, and
Yeah.
I can roughly understand why we are interested in semi-ample semi-ample type classes, but why are we interested in eigenvector classes?
Well, so what I'm going to try to do is understand the volume function near the pseudo-effective boundary on this variety. And I know 2 types of classes on the boundary. I know the semi-ample classes. I know those have numerical dimension 2, and I know the eigenvector classes, which have numerical dimension 3/2 if you allow these real numbers.
Sorry, and these are all on the boundary of the effective cone,
These are
right?
all on the boundary. That's right. So the semi-amples are, I mean, the birational automorphism group preserves things on the boundaries. Eigenvectors are automatically on the boundary by this Perron-Frobenius, basically. And these sums of 2 pullbacks of O1 are also on the boundary just because they're not big. You can compute the self-intersection. Yes, okay, so again, the eigenvectors are here. If you additionally throw in the semi-amples, they're occurring at the tangency points between 2 circles. Let me just tell you why am I not doing the things where you just pull back O1? Why am I adding 2 of them together? If you just pull back O1, they land right in the middle of one of the circles, and in fact, sort of slightly above it. So the pseudo-effective cone would include those. What I'm giving you is not a full picture of the pseudo-effective cone, but these are the more interesting classes. So again, the eigenvectors look something like this. There's these semi-ample type things which fit into one orbit under the birational automorphism group, and those fill in all these spots between two of the circles.
I guess another difference is that if you just pull back one of one, then its orbit is has cardinality 2, right? And for the other classes, the orbit is infinite.
All right, yeah, that's also, is that, I'd have to, how do you see its cardinality 2? I'd have to think it through.
I think it is preserved by 3 of these involutions.
Oh, okay. I'm sure you're right. I'd have to double check, but that would be another good reason to look at these other ones instead, I think. All right, so here's the thing that I found mysterious. Let me show you this picture, but a little bigger. So that on this plot, if you go around one of these circles, well, maybe I don't even need to blow it up. Let's say I go around this circle right here, this big circle. You can see my cursor, right? I'm very bad at zoom. Around this circle, there's both infinitely many of these semi-ample type classes, these red dots, and infinitely many eigenvectors, right? The same picture shows up in the eigenvector plot. So along this circle, it literally is a circle on the boundary of the pseudo-effective cone. You have both these things of numerical dimension 2, the semi-ample type ones, these red dots, and you have things of numerical dimension 3/2, the blue ones. All right, so this was very confusing to me. So let me just say again what the puzzle is here. If you take one of these semi-ample type classes, the volume of D plus TA is linearly growing in T. You know, there's some constant, the constant's different for different ones, but for one of those semi-amples, the volume of D plus TA grows linearly in T. For one of these eigenvector classes, the volume of D plus TA grows like T to the 3/2 power. So what could the volume, how is that possible, right? On this circle, the red ones, the semi-amples, and the blue ones, the eigenvectors, are both dense. Yet when you plot the volume, near a red one, it's supposed to grow linearly, and near a blue one, it's supposed to grow like T to the 3/2. And I'm not much of an analyst, so when I saw this picture, I thought we must be making some mistake. I mean, how could I have a function growing linearly at a dense set of points, but growing like T to the 3/2 at a dense set of points? You're all probably unimpressed, but it's a very strange behavior for the volume function, I think.
John, and can I ask like not a very precise question? So in this example and in the previous example, you work with threefolds, right?
Correct.
And why did we already know that there is no questions on the surfaces?
Oh yeah, great question. I should have said that's right. In the surface case, all these notions of numerical dimension are the same, and md plus a grows either constant m or m squared. So nothing bad can happen in the surface case. Threefolds are the first bad possibility.
And in particular, possibly, could you yeah, in principle, you could cook some example like the previous one in the two-dimensional case, maybe. But then,
yeah, so you could do, for example, you could even look at these Euler K3s and you'll get a similar picture. But what happens is that the volume.
Then you take the square root of m and square it, and then, right?
Yes, that's right. That's right. So you end up getting dimension over 2 in this kind of thing, in the simplest examples.
I see.
Yeah, so I mean, I got m to the 3/2. I don't know whether it's possible to get m to the pi power as the growth. I can't even get m to any irrational number. Yeah, but on the surface case, nothing bad can happen.
You can get any rational number.
I can't. I don't know a single example with an irrational number.
When it's irrational. And
I also see no reason it can't happen. I mean, it looks like it should be possible.
But you know also other rational numbers except for 3/2. Do you?
5/2. I can get integers over 2. That's essentially it.
I got. You mean in dimension 3 or in arbitrary dimension?
Correct. In arbitrary dimension, I have some formula that tells you what you get for a given pseudo-automorphism, so it reduces it to linear algebra. Every pseudo-automorphism I know, you get integer over 2.
Mm-hmm. I got it.
I mean, I think it would be very strange if that always happens, but who knows?
John, can you have 1/2?
No, so there's this Nakayama thing I mentioned way at the beginning. Nakayama proved that H0 of md plus a, if it's not bounded in M, grows at least linearly. So this 1/2 is excluded.
Okay. But then definitely when you can just multiply by P1 to get, to increase this by 1. So if
Correct,
you have
yeah.
3 over 2, then you can get anything over 2.
That's right, yeah. Any odd number over 2 you can do without too much work. Essentially nothing else do I know how to do it. I mean, let me even show you, there's a formula on a slide that I skipped. So if you have any pseudo-automorphism and it has the property that when you add the two eigenvectors together, the result is big, which is not automatic. This actually is, I mean, it's very common, but it's not always the case. But if the sum is big, you can do the same calculation and you get a formula, which is that the numerical dimension is the dimension of x times 1 plus log of the eigenvector of the inverse divided by log of the eigenvector to the -1 power. And what happens that's kind of annoying is that typically these two numbers, I don't think anyone has a good explanation, but in most examples, the map and its inverse have the same dynamical degree. So again, I'm not claiming that's a theorem or a conjecture. It's false. There are examples where they're not equal. But you know, what happens in most examples is these are equal to each other, so you get dimension of x over 2. So, I mean, a priori, these numbers really have nothing to do with each other. If there's no preserved quadratic form, which in higher dimensions there doesn't have to be, you know, there's no reason for these things to be connected. You should be able to get weird irrational numbers. I don't know a single example though. I mean, I know examples where this is irrational, but the sum is not big, so it doesn't help. Yeah, if anybody of you know a lot of pseudo-automorphisms, you know, take a look, plug it into that formula, and you can email it to me if you find something interesting. All right, let me go back to this mystery. So here's what I'm going to do now. So let me remind you where we were. We have this picture of a lot of classes on the pseudo-effective boundary. We use a dense set of them where volume of d plus ta grows linearly in t. There's a dense set of them where volume of d plus ta grows like t to the 3/2. So I'm going to make a plot of the following. I'm going to parameterize this circle on the boundary. So I'm going to get a parameterized family of divisors d sub t. And then I'm going to plot the volume of d sub t plus epsilon times a fixed ample as a function of t and of epsilon. And again, we're able to do this because on the computer, it can instantly tell you the volume of any divisor. So you can plot as many points as you want. You can get a good picture of the volume function. So this is what I had these students doing. Here's what we got. So let me try to explain this picture a little bit. So as you move along this axis from left to right, you're moving around the circle. You're looking at your parameterized family of divisors. As you move into the page, you're increasing epsilon. So we're looking at the volume of d plus epsilon a. So as you move this way, you change the divisor. As you move this way, you're adding a more and more ample. And so what you see right here, this corresponds to the, you know, the basic semi-ample. So at this divisor, when you start adding epsilon times a, the volume grows linearly, like I promised you, and we see that in the picture. It really does slope up linearly, you can see from the plot. And then these smaller ones, so if you take the orbit of that under some birational automorphism, you still see this linear growth. So if you took a divisor on the circle, this corresponds to another red dot on the circle. This is, again, growing linearly as you increase epsilon. And all those little red ones, you know, this dense set of points, you get linear growth. You know, the slopes of the lines are getting smaller and smaller. The constants are getting smaller. But all of those divisors have numerical dimension 2, which is reflected by this linear growth. On the other hand, there's also these eigenvector classes. Those are kind of far away from the semi-ample type ones. And those, you're not on one of these little bumps and it's growing like t to the 3/2, which is slower. Remember, t is small, so t to the 3/2 is less than t. So, you know, this explains this, what was to me a mystery on how could the volume grow linearly at countably many points. It's that the slopes are getting smaller and smaller. And somehow in between those points, you still get this t to the 3/2 behavior. Does this plot look okay on Zoom? I wasn't sure how it would show up. And again, this is the exact numerical calculations. I mean, up to 100 decimal places or something. So this is, there's no rounding error or anything affecting us. This is really what the volume function looks like on this variety. All right, so I think this is kind of interesting in and of itself. I hope you agree it's a fun picture. Let me tell you what let me show you a few more things related to this. So what if, here's a plot now as you vary the divisor around the circle and you add 0.002 times an ample and you compute the volume. And now what I'm plotting is not the volume, I'm plotting kind of the estimated exponent. So I'm taking the log of the volume of d plus epsilon a divided by log of epsilon and plotting that. So right, if the volume were growing like c times t to the d, if I take, this d should be, sorry, I mean, this is sort of my guess at the exponent. So again, I'm taking log of the volume of d plus ta. The students have been calling the volume f because they don't know what a line bundle is, but this is log of volume of d plus ta divided by log of epsilon, which is your guess of the exponent. So you're seeing that we guess the exponent to be 1 at these special divisor classes, but most of the time this formula guesses that the exponent is about 3/2. And so when epsilon is 0.002, you're kind of seeing this linear growth at these big red dots. You see someplace with more than expected volume, but the exponent hasn't quite come down all the way yet. Let's see what happens when you shrink epsilon, so you get closer and closer and closer to the pseudo-effective boundary. You add less and less and less ample. Well, let me go back and forth. Now you can see that there are even more of these semi-ample type things showing up on the plot. You get this bigger than expected volume, which causes the exponent to drop down. And so you see these tiny little points coming down. Then it's not getting all the way down to 1. That's because of the constant term times t. But each of these peaks at a red one is eventually going to come down to 1 as I take epsilon smaller and smaller. Now here it is with epsilon is 5 times 10 to the negative 5th. You can see more and more of these semi-ample type classes causing this smaller volume. Here it is with 10 to the negative 6. Picture starts to get a little messy here. But again, let me just go back to the picture. What we're seeing is that there is this very slow but linear growth at all these semi-ample type things that are dense, but you're getting this t to the 3/2 growth at the other things. And you sort of see more and more of these when epsilon is smaller and smaller and smaller. Any questions on these plots? These are my favorite part of this example that I have so far. All right, so let me state a theorem. I apologize though, I have a 2-year-old stuck at home with me and I haven't been able to check all the details yet. But what should happen is that there should be classes D for which you get this kind of oscillation between 3/2 and 2. So the volume varies between t and t to the 3/2. If you go to h0 instead of volume, h0 of md plus a should kind of go back and forth between m to the 3/2 and m squared as m increases. So I still have to write down the estimates, but it looks like it's going to work. If any of you want to ever quote this, though, send me a note and make sure it actually worked out. If anybody's watching the recording 10 years down the road, I mean, hopefully there will be a paper by then. So let me just tell you the idea of why this should work, and then I'll stop. The estimates are going to be a little messy whether they work or not. But
so once again, and x is still the Cantor-Giza-Calabi-Yau, right?
Yes, that's correct. It's this 2, 2, 2, 2 hypersurface in P1 to the 4th. I'm claiming, sort of based on this picture, that there are going to be classes where you kind of oscillate between linear for a while, 3/2 for a while, and so on. And the idea is, well, okay, let me tell you the basic strategy. If your divisor is close to one of these semi-ample things, then the volume is going to be kind of bigger than you'd expect for a generic D, right? You know, in this graph, let me go back to the graph again. There are kind of bumps in the volume graph when you're near one of these semi-ample type divisors. These little linear ridges correspond to the semi-amples. So if you're closer than expected to a semi-ample, then the volume is going to be larger than you would normally expect it to be. On the other hand, that doesn't work if epsilon gets small. You know, if you're within 0.001 of a semi-ample type class, then when epsilon equals 0.001, the volume is kind of bigger than what you think. On the other hand, if epsilon is 0.0000001, you know, that your divisor can't really tell that it's close to a semi-ample. I mean, the distance between D and the semi-ample is much smaller, sorry, much bigger than the epsilon that you're using. And so you're not really going to get for small epsilon, you're not going to get a boost from that semi-ample anymore. You're not going to get these extra sections. So if you're close to a semi-ample on some scale, the volume is bigger than you expect, on that same scale. But then you have to, when epsilon increases some more, you kind of lose this extra volume. Let me show you the picture one more time. And what I'm saying is if you're on one of these ridges get kind of narrower and narrower and narrower as you approach the pseudo-effective boundary. So if you're, this point right here, it sure looks like it's close to this semi-ample class, when epsilon is fairly big. But eventually this thing kind of narrows into a point, and so that one's not going to have any extra volume really coming from that semi-ample when epsilon is small. All right, what you want to do though to get this really bad behavior is take divisors that are unusually close to semi-amples at many different scales. So I think the way to think of it is this: those semi-ample classes, they're kind of a countable set on this piece of the boundary of the pseudo-effective column. They're kind of like the rational numbers. And so you want to find a divisor that's sort of unnaturally close to many of these semi-amples at many different scales. So the analog in terms of rational numbers would be look at something like a Liouville type number that's the sum of 1 over 10 to the k factorial, right? That's really, really, really close to a rational number. There are many, many different rational numbers, infinitely many, where it's closer than you'd expect it to be to any rational number. It's too well approximated by rational numbers. So you want to do kind of the same thing. You want to take a divisor, on this piece of the pseudo-effective boundary that's close to many of these peaks. It's close to many of these semi-ample type divisors, much closer than you would expect it to be. So it should be possible basically using a construction almost like the Liouville numbers. But again, I apologize. I shouldn't be claiming this as a theorem in public until I write it all down, but it looks good, I think. So there do exist kind of analogs of Liouville type numbers on that boundary, and you should see oscillating behavior for these things. And what kind of general statements can you hope for that? I'm not really sure, but somehow the behavior of H0 of MD plus A in this type of situation is going to depend on the Diophantine properties of the divisor in a very subtle way. How close is it to these semi-ample type classes, which give you this faster than expected volume growth.
And sorry, did I get it right that, so if you find such a miraculous divisor, then you hope that d plus epsilon times a, so to say, passes nearby several semi-amples.
That's right.
Many semi-amples, and in infinitely many epsilons, you have this boosting of.
Correct. Yeah, let me show you one more picture. So going back to the graph, I've sort of been talking about hills here. I'm going to draw you a plot of all the divisors where the sort of expected exponent is bigger than 1.4. So it's going to be sort of an approximation of what are the locations of those hills in the plane. So this big blue area here, this is that main central hill you saw on the plot. But you can see as epsilon gets smaller and smaller and smaller, it narrows into a point. So a divisor that's marginally close to that semi-ample does, lie on that hill. It gets a volume boost for small t, but once epsilon gets smaller, this is log epsilon, and going up epsilon is getting smaller. Once it gets smaller, well, then the kind of extra volume disappears, and the sort of calculated exponent just falls back down to 3/2. But you can see there's still many, many smaller hills that are corresponding to semi-amples near there, but with much more complicated birational automorphisms and slower linear growth. So what these Liouville type things are supposed to do is, it's on this hill for a little while, then it disappears, then it gets on one of these other hills because it's really close to another semi-ample, just like it's close at some other scale to another rational number, gets some extra volume for a while, it looks linear for a while there. As epsilon gets even smaller, it falls off that hill too, because all these hills narrow in. But eventually at some other scale, you're going to get another one. It's going to get this linear growth for a while, then you lose that, and this should give you this kind of oscillating behavior. Yeah, but again, sorry, watch for the paper before you quote me on this. But I think it's going to be okay. Yeah, so the result of this in terms of kappa sigma, assuming it works, is that kappa sigma plus can be 2, while kappa sigma minus is 3/2, or is 1 if you insist on integers. All right, this seems like maybe a good place to stop, but I'm happy to take more questions.
In your counterexample, the class D is the irrational class. So is it possible that the conjecture is still true if D is the rational pseudo-effective class?
Yes, I have no example that's an actual divisor instead of an R divisor.
Oh, okay.
In fact, any construction like this has this danger that, I mean, these eigenvectors have to be irrational. So you're never going to get a rational counterexample doing something like this.
Mm-hmm.
So you mean that this from this construction you don't get rational counterexamples, but still, what's your expectation about them?
Oh, I mean, I assume everything is false, probably, but yeah, I wish I had a rational counterexample for anything like this, but somehow these constructions never give one. So I'd be surprised if it's true, but who knows?
And maybe another question. So you said that there are around 15 definitions, and so you managed to show that 2 of them are in general give different numbers. Do you know about these differences for some others as well?
No, yeah, so it's possible some of these are equal to each other. That I'm not sure. The story, so the way they were originally proved to be equal was kind of amazing. So he had 8 of these definitions, and he proved a circle of inequalities between these definitions. And it turned out that just, and then of course you conclude they're all equal. It turned out there's a small mistake in just one of these inequalities. So the circle still turns into a linear sequence of 8 of them that you have in order. So I think my example sort of cuts it in the middle somewhere. Some of them are 1, some of them are 2, some of them maybe you want to be 3/2. But there are still many correct comparisons between these things. Yeah, but I don't have ways to distinguish all 15 or however many there are.
Great. So other questions?
So what if D is a canonical class which is still effective?
I mean, in that case, for the canonical class, you expect that kappa sigma is the same as kappa if you believe abundance. So nothing bad should happen.
Yeah, but you plus the M class A here.
Wait, sorry. So you want to take D to be the canonical, or?
Yes.
Yeah, I think in that case, if you believe abundance, it's probably known that H0 of MD plus A is just going to grow like M to the codiro dimension.
Oh, okay.
So
unfortunately,
15 of them, right? All 15 dimensions are equal to codiro dimension.
Yeah, so it's conjectured that for the canonical class, kappa sigma is equal to the codiro dimension kappa.
And so you say that this is true modular abundance, right? Did I get it right?
Never of the form kx plus delta for a KLT boundary delta. So these kind of bad behaviors you're getting are never quite of the type you would want in the MMP. I mean, if you're trying to disprove the MMP, this doesn't help. These are strange divisors that are not canonical plus something nice.
Mm-hmm. So any other questions?
All right, well, if anyone has some, I'm happy to hear by email too. Or if you're interested, I can send you a draft of these bounds once I check everything. But yeah, let me know if you're interested for sure.
Yeah, then let's thank John again. So I would say that for many years, while the seminar was running, I think we never had the same or even approaching number of graphs and plots in the seminar talk. And
Yeah, I'm kind of lucky. This is a good one to do on a computer.
it shows us that mathematics is still an experimental science, which is good, of course. And, and also many particular examples also very good. Thank you. Thanks a lot.
Thanks.
Thank you.
Thank you, John.
Thank you.
Oh, hopefully I'll see you soon, Yuri.